This is the Kratos Concept Electron Impact Magnetic Sector High Resolution Mass Spectrometer. The instrument has a calibrant, PFK, that runs through the instrument at all times, making sure that every scan is calibrated by 83 known exact masses. This scan shows a small mass range around 219 Dalton. This PFK peak is used to optimize the voltages within the source and to physically narrow the slits in the instrument to produce the narrowest peak possible. And you can see that this peak is less than 0.05 Dalton wide, producing a resolution near 10,000. We try to achieve this resolution every time we run the experiment. This then allows us to use the accurate mass data acquired when running a sample to verify the molecular formula. And here's how that is done. Forms for all samples can be downloaded from the website or picked up in the facility. This is what an electron impact form looks like. It is especially important to draw out your molecule and to add the formula and the molecular weight expected. For the concept, a pure solid sample of the compound is then attached to the form, and it can be placed in the EI inbox on the shelves just inside the facility's main door. If you have an organic metallic compound or something that is slightly unusual or you're unsure of, please talk to me. The concept source block has a heater that runs to about 300 degrees centigrade. So if your sample has a boiling point higher than this, your sample will not go into the gas phase, so please use another method of MS analysis, maybe electrospray. And the magnet will scan to approximately 800 Dalton. Again, if your mass is higher than this, use a different method. The sample must also be pure. There is no pre-separation technique on this instrument, so the sample must be pure. If you have a mixture of compounds, use the GCMS instead. So, how does it work? The source of an electron impact instrument contains a filament. Electrons created at the filament are accelerated to 70 eV, and they bombard the gaseous sample created in the source by the heater. The electron beam knocks out and ionizes an electron from the sample, creating a radical cation. The ionized ions can then be accelerated into the mass filter, the magnet, for further analysis. This form has been filled out correctly and also shows a possible mass for a likely fragmentation product. Phillips sample is taken out and a small amount is placed inside a glass capillary that is inserted at the end of a probe. An electron's impact source is within the interior of the vacuum, so to get the probe into the source, the vacuum is broken and restored in 2 stages. The probe is first inserted into the extension to the source, which is separated from the main source interior by a gate. This section is brought up to air by first turning off the roughing pump and then opening the section by removing this bung. The probe is then carefully inserted into the hole, which seals it, and the roughing pump can then be turned on and the pump gauge is monitored to see the decrease in pressure. This section is now pumped down to approximately 10 to the minus 3 millibar, and the gate between the source and this section can now be opened. The source ion gauge can be seen to increase because of the sudden increase in pressure in the source region due to the difference in vacuum between the roughing pump vacuum and the source vacuum, achieved by a turbo pump of 10 to the minus 7 millibar. Once the gate is open and the pressures have stabilized, the probe can be inserted into the ion source block, and this can be adjusted and monitored through a window in the side of the source housing. The software on the instrument acquires mass scans that can be monitored. This shows the mass spectrum acquired by Phillips molecule, and we can see lots of peaks. The one at the highest mass should correspond to the molecular ion, and the rest are fragment ions created by the molecule being hit by the 70 eV of electron energy. EI is described as a hard ionization source because of this. The molecular ion looks like it occurs at 552 Dalton. Phillips molecule, as we can see from the form, has a mass of 552 Dalton. Bingo! Because of the calibrant and the mass resolution of the concept, we are able to use the instrument software to determine what molecular formulas are within a few millimass units of this molecular weight. If Phillips' expected formula is within 5 millimass units, it can be stated with confidence that he has that particular compound. These results can then be published. The instrument has found 3 possible formulas that add up to that mass, and the bottom one is Philip's molecule, and it is within 0.6 millimass units from the expected mass, which makes it publishable. Well done, Philip.